Chase. First, I'd like to introduce Cho. The Cho is an aerospace engineer in Cryogenics and food branch at NASA Goddard Space Flight Center. This is on our driving from here. And Chase got a bachelor's degree from Seoul National University and also the master's degree as well, with a concentration of precision and engineering and manufacturing and mechanical and aerospace engineering. So you might get a sense that he's an engineer, so I think he just got well. After graduating from Seoul National University, he joined the Korean Institute of Industrial Technology as a research engineer and in the robotics and R&D groups. And he did multiple projects for 3 years. And he developed the low-cost, flexible tactile force sensors, artificial biomimetic flow sensors for robotic fish, and biosignal monitoring sensor models for robotic aid for soldiers. Then Chase returned to academia in August 2016, and got a PhD degree in 2021 with a concentration of the strain and interfacial engineering of 2D material for flexible and optoelectronic applications at the University of Illinois, Urbana-Champaign. And that's where I met with Chase actually. And I was doing this postdoc 2014, 2017. He was selected as a NASA Space Technology Research Fellow in 2017. He will be talking about the fellowship opportunity at the end of this talk as well. But as a fellow, Chase has completed 2 rotations at NASA Langley Research Center 2018, working on the boron nitride nanotubes for the radiation shielding study. And he got award the Sectional Contribution Awards and at NASA Jet Propulsion Lab in 2019, working on the surface acoustic wave for tunable optical braiding. And then joined after he got a PhD in 2019, Cryogenics and Food Branch at NASA Goddard Space Flight Center. And then he became a full-time employee in 2022. And he published many papers and co-first author, and received the patents and the main inventors and awarded a gold winner of the Graduate Student Award from Material Research Society. That's one of the prestigious awards awarded to the graduate students in material science and engineering field in 2020. And Chase's technical interests include the material fabrications at cryogenic temperatures, quantum optoelectronics, and thermal control, local cooling of optics and electronics. So today we'll be just sharing this research accomplishments with the title Strain and Interfacial Engineering of 2D Materials for Flexible and Optoelectronic Applications. So please give me applause and
All right, thank you for the introduction and thanks for inviting me to give a talk to quantum sensitivity. So my name is Chullhee Cho. You can call me Chase. I'm an aerospace engineer in Cryogenics and Food Branch at Goddard Space Flight Center, located in Greenbelt, Maryland. So today I'm going to talk about, actually it's my PhD work. It's not related to Cryogenics branch because as you've heard, I'm kind of like an early career in this branch. But I'm going to touch a little bit based on what I'm supporting in terms of missions at the end. But yeah, today I'm going to talk about how we can introduce advanced functionalities for optoelectronics and flexible electronics by manipulating interfacial characteristics and the deformation of 2-dimensional materials. To start the talk, I'd like to give a brief intro of our NASA Center, Goddard, and our branch. Then I jump into research, what motivated me to work on 2 research areas of flexible electrode with 2D interfacial engineering and strain tunable exciton system. And at the end, I believe the general audience here is a student, so I'm taking this opportunity as an outreach to give you guys some sense of what are the research opportunities you guys can pursue with the NASA scientists here. based on my experience as well. So starting with the NASA Center, excuse me, we have a 10 different NASA Center across the nation with the specialties. For example, like Johnson Space Center located in Houston. They're in charge of all the space flight operations. That's why you're here in Houston, electronics, right? And Kennedy is where we launched the space shuttle, and we have a headquarters in Washington, D.C. And I'm from Goddard, located in Greenbelt, Maryland, where we lead almost most of the science mission and science instrument, especially for telescope. So speaking more detail about Goddard, the Goddard Space Flight Center is named after the scientist Robert Goddard, who's a pioneer of liquid fuel rocket. And Goddard is actually the largest organization having like 10,000 scientists, engineers concentrated in one organization, including civil servant and contractor in the U.S. So what that means is if you come up with an interesting idea, there's a lot of people who can help you out with their expertise. And I mentioned that we lead most of the science mission telescope. I believe you guys heard of Chullhee Space Telescope and James Webb Telescope, right? So adding a little bit of my experience with Hubble telescope, a story there. So when I started at Goddard, my mentor, Dr. Dave Laceworth, was an astronomer. We just chat about the deep space, which as a mechanical engineer, I had a chance to get exposed myself to like astrophysics and heliophysics that much at the moment. We just talked about random stuff. And at the moment, Hubble released a vast amount of these images for their 30th anniversary of the mission. So I just want to talk about this one image, which I got so amazed about. This image captured the dynamic moment of burst and the death of the star at the same time in one frame. So starting with the burst of the star, this middle plot, there's middle portion there. There's a white dot, which is like 10 times massive than the sun, and because of a strong radiation, it glows the nearby gas in a stunning color. So the red indicates there's a presets of nitrogen, hydrogen, and blue indicates like oxygen there. The nearby nebula, this blue nebula lower left corner here, is showing you the depth of the burst. So material is actually ejecting out of one star in the middle, which is 2,000 times brighter than our sun. So this was really interesting image to me. And on the right, I'm showing you Goddard Space Flight Center, where we have this nice mirror of the James Webb Telescope assembled in a huge clean room. And this is actually where I have my office here. It's not, the office space is not as fancy as you do here, but at least it's good to get some feeling of it. All right, so talking about my branch. So our branch at Dr. Eric Sills, I believe, gave a talk in March and give a pretty good overview of what we are working on and also about the NASA. But for those of you who are there, I'll just give a quick introduction. Starting with the cryogenics. So the origin of cryogenics, the cryo comes from cold, and genics is generation. So basically, we're making the environment cold. One of the warm greeting that I thought when I joined the group was, "Hey, welcome to the coolest thing in the universe." I was like, "What do you mean?" We're the ones who can cool down the temperature, the lowest temperature in the universe. I was like, "Oh, that's cool." And the first question people ask when we talk about cryogenics is, like, how low do you define as cryogenics? So according to the National Degree of Standard, temperatures below 123 Kelvin is defined as cryogenic temperature. And within our branch, we have 35 boys, including engineers, technicians, faculties. And what's our major role at Goddard is we support all the cryogenic space flight system engineering. And in nature, it includes a lot of multidisciplinary work. So we have people from all different backgrounds, like physics, aerospace engineer, mechanical engineer, computer science. And having said about James Webb Telescope, our team is taking lead of providing guidance support of cryogenic INT. And since this is a quantum thing, I try to make some connection here. So when we go down to the low temperature, there's a lot of interesting aspects, like in terms of material elasticity, it becomes stiff. But for the quantum effect, there's a really interesting happen. In the low temperature, one of example would be circular, like helium-2. You get like zero viscosity at the low temperature, which means there's got to be no friction moving around the fluid. And superconductivity is one of the really popular areas these days. Your resistance becomes to zero at low temperature. And actually, a lot of detector folks that started taking the superconductivity in terms of detector technique. The TES stands for transition edge sensor. So when you reach to the transition temperature, you expect to see a really strong spike in the resistance. So what that means, with the small amount of heat that is coming from, it's actually used for bolometer. So with the small amount of heat that is generated by the instant photon, you can detect by the increase in the resistance. So that's about TES. And NFIT is microwave kinetic inductance detector that's also operating at 1 Kelvin. So they need fraction of temperature, and that's what we are supporting. And also, we are superconducting interface device for the magnetic field is also a popular area. So in terms of physics, when we go down to low temperature, we can reduce thermal noise a lot. That's how we can increase the signal to noise and the sensitivity for the detectors. For example, bolometer scales with the temperature of this scale. So if we cool down the temperature, we're able to define the hidden peak that we cannot see at the room temperature which we're above. So today I'm going to talk about a little bit related to quantum that I did during my PhD. Jumping into research, I prepared 2 topics, but I guess second topic is more informative to you guys, and you guys might be interested in. So I'll be quick on the first topic. So I'm taking 2D material, 2-dimensional material as fundamental building blocks throughout my study. And the first question will be, what is 2D and why am I interested in 2D materials? To give you a brief description, 2D materials are atomically thin, layered crystalline material that held with strong in-plane bonds with a covalent bond and held by weak interlayer van Waals interaction. And on the left, I'm showing you one of the popular description of 2D materials repeated as a Lego block. So what that means is we can selectively assemble a various combination of 2D materials such as semi-metallic graphene or insulating exciton or nitride or semiconducting transition of the tricosanides to a concept of selenide. So by doing so, we can create innovative multifunctional devices. When we go down to the model layer, it only held by strong in-plane covalent bond, which give us high mechanical strengths with high elastic limit. And because of atomic thinness, it exhibits low bend excitness. In other words, easy to bend. So to give you a more intuitive description, a single layer of carbon atom, which is graphene, it exhibits 100 times stronger than steel, and even 1,000 times stronger than graphite, which you can find in the material at the tip of your pencil. And a single layer of graphene, monolayer graphene, can withstand a weight of football. I thought this was an interesting description. In addition to this mechanical property, it also has attractive electrical property with a high mobility combining with low bending stiffness. So high mobility, easy to bend, it became an attractive candidate material for flexible and low electronics. However, because of the atomic thinness, I'll say floppiness, the 2D material can be strongly affected by external stimuli. So even though you think it's a flat graphene, there's like uncontrolled out of deformation of corrugation or rippling present in a graphene because of thermal fluctuation. So from the synthesis to transfer processes, in order to minimize total energy in response to the external stimuli, 2D material tends to form into out-of-plane deformation in the forms of wrinkles or buccal delamination or bubbles. So people have been trying to make what they call ultra flat graphene by depositing on various substrates. But still, this type of uncontrolled out-of-plane deformation have been considered as topological defect that giving anisotropic material characteristic, or even failure that deteriorating the mechanical integrity of 2D material-based systems. So people have been working on to control this type of out-of-plane deformation to enhance functionality. For instance, by utilizing chromatography, we can enhance the electromechanical robustness. So we can improve the stretchability without impairing electrical resistance. Also, we can enhance the light-matter interaction, resulting from the increase in areal density by chromatography. It's actually a premier work done by Professor Kang here. In the below, also showing you that theoretically, it's predicted that we can modulate the resonance of the light by changing the topography of the wrinkle itself. Another interesting area is when we integrated this type of particle structure into field effective transistor. It is reported that one of the highest detection sensitivity of biomolecules resulting from the formation of electron hotspot at the belly of the particles. Another popular area is that with the mechanical straight, we can choose the electronic band structure, especially for semiconductor material like traditional triphosphonite, which I'm going to talk about in the later slide. And this is one of popular area called NDF engineering. So we know that structural or straining tuning can be effective too, and it's in use in advanced functionalities. So starting with the first topic here, titled as strain resilient electrical functionality in thin film metal electrode using 2D interlayers. Before I start, I can take a brief moment to acknowledge all of my great collaborators, including Japan here. So before I move on to, I will click on this topic. Before that, I want to throw some keywords. I'm going to talk about metal, which is one of the best conductor and cost effective for the process, and flexible electrode. And you can connect that to metal will be under deformation that we'll expect to see some cracks, okay, because of the brittle nature of the metal. And people think the cracks are mostly a bad thing, things to avoid, right? What we discovered here is that if we can manipulate cracking pattern in a certain way, then we can actually take advantage of it and reduce the new functionality. And behind that, 2D material, one atom thick layer of 2D material is a game changer. So we're interested in flexible electrode, which has been considered an essential component that opens up all kinds of new possibility of electronics, spanning from our daily devices like mobile smartphones, like display, wearable health monitor devices, and to further offering opportunity to diagnostic on curvilinear layer interfaces. So ideally, flexible electrode requires those high electrical conductivity and mechanical flexibility. In this regard, thin film metal on flexible substrate has been ubiquitously utilized for advanced flexible and wearable electronics. However, during their practical uses, we often experience unexpected failure of the device, then the device becomes frustratingly unusable. Because of the brittle nature of metal, rapid surface crack develop under various deformations. And after the onset of a metal fracture, this in-plane crack extension across the metal filament causes catastrophic failure of complete disconnection that severely reducing the functional lifespan of devices. So to address your challenges, we start with a relatively simple idea. Why don't we just insert 2D materials because we know it's high strength material with high toughness? Then the result turns out to be much more interesting than that. We observe a strikingly different packing patterns with the underlying graphene layer, shown at the bottom left, schematic compared to conventional metal on the right. And it was really intriguing to see that how this microscale phenomena of pack behavior or pack modulation can contribute to the macro scale of electrical performance as shown in the plot. So we observe there's an elongation of strain, or elongation of resistance with strain, which we going to turn into electrical ductility. So this is analog to mechanical ductility that defines the elongation of material deformation with strain. So our metal to the electrode exhibited extended region of strain resistance with the resistance level reduction of several order of magnitude compared to the conventional metal electrode. So I'll just move on to this. So we just look at the fracture surface of metal. Why we're seeing this type of phenomenon. So on the top panel shows a series of XM images comparing the pattern behavior under bending deformation. The top three panels shows conventional metal electrode architecture where we have thin film of gold, a digital layer of titanium of PDMS. On the bottom, we insert a graphene at the interface. As you can see, without graphene, we see the crack propagated and straight and resulting in a relatively large area of isolated fracture domain. However, with the graphene, crack propagated with local zigzag fluctuation, resulting in tortuous cracking behavior with the polygonal interconnected fracture domains. A little bit of quantitative analysis. With the fracture domain side, we saw there's early saturation of fracture domain side in case of gold without graphene, whereas we observe there's a continuous or progressive reduction in the domain size in case of gold with graphene. So this type of early saturation of fracture domain size indicates that there will be no strain energy dissipating through the cracking. So the excessive strain energy goes into interfacial fracture that may cause this type of debonding failure. Another interesting observation was that metal 2D or gold graphene electrode maintain their electrical conductance at above a strain where the conventional metal electrode shows complete disconnection. So this motivated us to look into the strain-dependent electrical performance, which I'm going to talk about in the later slide. But here, we observe a distinct different fracture behavior with the underlying graphene layer. And this raises a very interesting scientific question that from the previous study, we learned that both metal and the graphene shows relatively brittle fracture behavior. But when we layer these two materials, they show relatively ductile fracture behavior, indicating that there's got to be an external mechanism play role into this type of phenomenon. So we look into unveil the mechanism with the support of molecular dynamic simulation of the collaborators of Professor Lulu from U of I. We revealed that after the metal deposition, there's a formation of heterogeneous buckle network in the film. And that's because by inserting 2D material, we're changing the film property. You're increasing the modulus, so referring to the space diagram of the formation of structure and surface stability. This denomination buckle is what we're interested in. So by inserting this high strength material, we're increasing the modulus ratio. And at the same time, due to the lack of dangling bond on 2D materials, it's only held by van Waals interaction. So we expect to see there's a reduction in the region, so it's going this way. And in terms of strain, we're only talking about some thermal residual stress that can happen during any type of metal deposition, resulting from the mismatch in the thermal inspection coefficient between the film and the substrate. So with that, it's more favorable to form into the laminated buckle, and we confirm that with our molecular dynamic simulation and stuff. So directly jumping onto the mechanism part, which we call buckle-guided fracture mechanism. They're covered by this kind of there, but yeah. So as a step one, after the metal deposition, we saw there's like a heterogeneous buckle network formed on the surface. By looking at the cross-section, we're able to estimate the accumulated strain of the press of the buckle, which is around 1.1 to 1.3%, indicating that the press of buckle are susceptible to initiate the fracture compared to the non-buckled area. And that's what's actually happened in the next step. Cracks are preferentially initiate the press of the buckles and propagated along the heterogeneous network, and resulting in this fortress cracking behavior. And multiple cracks interact and intersect each other, effectively delaying the complete disconnection of metal film. And we also observe multiple spots of this crack-reaching area that is contributing to forming this effective conductive path through the fracture surface. So we deduce that this discrete buckle network can effectively glide crack passes and a perturbed in-plane crack extension, resulting in macroscopically ductile behavior. So now we look at how this modulated cracking behavior can contribute to the electric performance with the various deformations. On the top panel, I'm showing you that under bending deformation, as in the schematics, we see the electrical ductility behavior, where we saw this elongation of resistance with strain and also reduction in the resistance compared to the conventional metal. And in terms of electrical failure strain, when we add like full layer of gapping, that shows more than 400% improvement. And this was similar to the twisting deformation as well. We saw this nice this electrical ductility behavior. And also under repeated mechanical loading, it shows robustness as well. Not only tested with graphene, alternative layers like MOS2 or hexagonal nitrile, which is the insulator. So this confirmed that 2D interlayer play a key role to induce this phenomenon regardless of their conductivity. And also it's not limited to certain combination of metal or 2D materials. So at the end, we demonstrated our general optic capability by creating flexible light emitting device and demonstrate the augmented durability of the various deformations. So we monitored the luminous power as a function of bending strain, and with conventional metal, there was a sudden drop in luminous power. Whereas we observed a gradual decrease in reduction in luminous power, and this enabled us to have a capability that we can detect the damage in the early phase. What I mean by that is we can alert the user that if you see like 50% reduction in luminous power, you need replacement or partial maintenance. In terms of device failure shift, where at a strain the device became unreadable, the conventional metal electrode integrated device, the metal to the integrated device shows about a 400% improvement compared to conventional metal. So just moving on to the summary, it was really interesting to see that how this one atom-thick interlayer can change the cracking pattern of metal on top, induce unique characteristic of electrical ductility that's substantially improving the electrical performance under the strain application. All right, I want to switch my gear to the second topic, which you guys will be more interested in. So here we explore how the strain effect on the interfacial characteristic specifically interlayer coupling between the layers, and how does it affect on the emission characteristic of interlayer exciton. Again, I'm going to take a brief moment to acknowledge my great collaborator. This was done by Professor Harry Atwater at Caltech, and also Professor Nara Alulu and Sarana from ULI. So among the 2D material layers of classical transition metal to tripolymer, which are semiconductors. And for the model layers, for example, modulation concept of selenide, they have a direct band gap, and that exhibit encouraging light-matter interaction over the visible wavelength range. And when the material absorbs a photon energy that has a larger band gap than its own band gap energy, then it excites the electron from the valence band to conduction band. And that creates this electron hole quasi particle there, bounded by Coulomb interaction, which is called exciton, and arising from the low dimensionality. What I mean by that is, when we go down from bulk to two-dimensional, we can substantially reduce the dielectric screening event, which will give us this large excitonic binding energy. This is actually enable us to realize the excitonic device operable at room temperature. So just to give us some terminology here, when the electron hole quasi-particle created within the layer is called intralayer exciton, and when it's created between the layer is called interlayer exciton, which is a particular interest of our study. So the first observation of interlayer exciton in Boston-Townsend deselenide heterobilayer system was reported in 2014 by Elijah V's group, where they observed emergence of a new peak, photoluminescence peak, in the energy redshifted by 75 million electron volts in relative to the A exciton energy of constant deselenide. And the mechanism they reported in the paper was that first, the constitutive monolayer observed the photon energy and create this electron hole pair. And because of the band offset in this type 2 band alignment, the electron and hole drift to the atomic interface, and they recombine into. Is this temperature data? Yeah, this is the they drift to the atomic interface and recombine into interlayer exciton. And this platform has been of real interest because we can study the charge collection, charge separation mechanism, followed by the photo objection and photodetector or solar cell. So the first demonstration of excitonic device operating at operating at room temperature is demonstrated in 2018 by NJRT's group, where they utilize the unique characteristic of interlayer exciton having a vertical dipole moment. So by they manipulate the flux of exciton by applying electric field using the Stark effect. So I'm interested in this particular combination of positives when it comes to deselenide. Why is that? Because they are relatively less twist angle sensitive. So when we talk about 2D materials, when we stack up the different material, there's additional tuning of the twist angle. But if the combination is so sensitive about twist angle, then we cannot claim that other tuning that we're interested in this case, the mechanical straight, cannot be the major role here. So that's why I choose this platform, less twist angle sensitive. And another interesting characteristic of this platform is that we can observe momentum space indirect interlayer exciton, which means there's an optical transition between the gamma and K value here because of the band hybridization at the gamma point. So as you can see here. So to give you a little more explanation, optical transition is allowed in K gamma value transition because of the band hybridization, but as opposed to KK value, where the dipole matrix element is strongly suppressed between the unlike state. So with this interesting interlayer characteristic, we want to explore more rich information by adding one additional tuning knob of mechanical strain. So when we apply mechanical strain to a 2D material, we can change the in-plane orbital interaction, and that can change the electronic band structure. Oh, so that can be described by the deformation potential theory. Here, additional Hamiltonian related to strain can be introduced, and by solving the eigenenergy, we can get the band structure as a function of strain. For example, if we apply tension loss to the energy at the K gamma value is energetically lower than KK, so there's an optical transition from direct to indirect. And that can be seen by the photoluminescence measurement. So what you're interested in is what will happen if we layer these two materials. Is that? What is what? Oh, this is separation potential constants for the so at the end we experimentally derive this constant as well. If we don't have a time, I'll just skip the fabrication process. It's just talking about creating the bilayer, achieving the ultra clean interface, so just a quality fabrication. I think I need to go over this. So with the pre-strain release mechanism, we can create this type of wrinkle structure. So we pre-stretch the bottom substrate, deposit our target material. Once we release it, the compressive strain induces this type of wrinkle structure, inducing local stretch of atomic lattice at the crest, inducing tension and relative compression at the belly. So after creating the wrinkle structure, we conducted confocal PL mapping, showing that there's a substantial pinching at the heterojunction, indicating that we're creating decent interlayer coupling because of this ultra-fast charge transfer phenomena in such type 2 band alignment. So in order to probe the strain effect, we look at the spatially probe the photoluminescent energy of a represented wrinkle, including both intralayer, and interlayer exciton. I'll just move on to the interlayer exciton because this is more common phenomena into the articles. So we observe really a remarked qualitative difference compared to the intralayer exciton. We observe greater tunability and also non-monotonic behavior of PL intensity, where we observe this maximum intensity at the intermediate state as opposed to either crest or belly in case of intralayer exciton. So we're curious about why this is happening. We turn to the Raman spectroscopy, which is a direct measurement of the strain effect. So first we look at the E to G mode, which is sensitive to the in-plane vibrational mode. And it says that there is a tension at the crest and the compression at the belly. So this is somehow expected. Then we look at the local strain effect on interlayer coupling by looking at the mode separation of A1G mode and E2G mode of MOS2, which can take as a mechanical quantitative measure of interlayer coupling strength in artificial spec bilayer MOS2. So the larger mode separation means stronger interlayer coupling. So by taking this line profile of multiple couples, we get these mode separation change from 20 at the crest, where we think there's like a strong in-plane tension, and smaller mode separation at the belly, we expect to see less tension there. So suggest that stronger interlayer coupling at the crest and weaker at the belly. So you can think of it like a Poisson-like effect. When we tool the material, we expect to see reduction in the thickness, right? There's a strong in-plane. So then when there's a strong in-plane tension, we expect to see stronger interlayer coupling. So this is just a theoretical support that is very interested in PL intensity. We correlate that to the oscillator strengths there and supported that at the belly, interlayer coupling becomes weakened, so that there's a reduction in the oscillator strengths that gives us reduction in PL intensity. However, at the crest, interlayer coupling might be sufficient, but then in-plane tension also modulate the band structure, give us reduction in the oscillator strengths and result in PL intensity as well. So back to your question, we derived the DIJ parameter here with the experimental data by using Brunner's parameter from the Raman and the photoluminescence energy shift. Compared with the theoretical data, conclude that this interlayer exciton is really highly strain sensitive. And also what we contributed to the community is that this interlayer coupling can be an additional strain tuning knob for multi-layer excitonic devices. Actually, I think this will be the most interesting for you guys. I just want to share the research opportunity they can pursue with NASA scientists in different locations. So first is called an STGR Fellowship, stands for NASA Space Technology Graduate Research Opportunity. If you're like citizen or permanent resident graduate student, if you have a creative idea that can contribute to space technology, then you just definitely apply for this. They supported up to 4 years. And one tip, and it offered really nice multiple rotation work with the different centers. it's up to you. You can choose which center you want to work with. So in my case, I worked with NASA Langley in Virginia and JPL in California. Those really like to get some sense of different working environment, different topics as well. So one tip based on my experience, when you apply for this, look for the keywords on the website. So they, NASA's interested in a particular area, a different area, different years. So I realized that after I got selected this fellowship during the seminar, there was like, so I was selected in 2017 and I attended a seminar in 2018. They were presenting this slide having keywords for 2017. And I just realized that I had all the keywords in my title. So I was just lucky to have all of it. So if you can, during your free time, just search for the keywords that NASA released and try to involve in your title, and at least in title, and that'd be great. Another one is more like a long term, as a converting you into a full-time employee from the field. This apply for undergrad grad proposal. And this offers multi-semester experience for your selected branch, so you can get some sense of the working environment, the type of work that you're doing. They usually post on usajob.com. So one aspect of this is NASA wants to hire a lot of good students, but then this program is not advertised much. So it's more like a lack of information for the students. So, just look for this keyword, and I think for you guys, like local students nearby the NASA Center, also have different opportunity for interns. So go into this site and look for the opportunity, and you can get some good hands-on experience at the NASA Center, especially only on our way from here. Speaking about the internship opportunity, this is one of the projects that I'm supporting. The title here is Multifunctional Sensor Platform, short MSP. NASA like acronym. So MSP, the principal investigator is Dr. Melissa Sultana. This is email address for her. She is very open to hire students to work with as a summer intern or pathways. So if you're interested in this type of sensor technology with the nanomaterials, it's a really good opportunity. Just to give you a brief description, we know that nanomaterials are good, like in terms of sensitivity, but the drawback is that there's really low yield, low reproducibility, and a high labor intensive, which means if you look into the papers about 2D materials or nanomaterials, one graduate student took a lot of time to make one successful device and publish a paper. That's how it's really hard to make the device, complete device. But here, the aim is that to make all the process automated, 3D, like a 3D printing, edited technology. So here on the PCB board, we print out pressure sensor, chemical sensor, temperature sensor, with some communication device to transfer the data. And what this is good about is we can detect like ammonia as well. So for the capturing the biosignals in different planets, we usually use this huge mass spectrometer. But this innovative idea can contribute to the small instrument they can detect, used for detection of light signal. And this is planned to be mounted on International Space Center for environment monitoring, and also mounted on the lunar rover for Artemis program. What's that? Is there what? James Webb? Oh, this one? Yeah. Okay, so not yet, but we can proceed for that. So another project that I'm supporting is ExoMars, in short, AMOMA, Mars Organic Molecular Analyzer. It's supposed to be launched in 2023, but they got delayed forever because of this ongoing war. Anyhow, just to give a sense of it, we want to detect the light signal from the Mars, but from the Martian soil. But then the surface was damaged by strong radiation. So we drill down the soil, collect the sample, vaporize it, and then we enter the mass spectrometer to get the species out of it. I'll just skip this. I was just going to give some suggestion on perhaps yeah, that's all about it. For the last we are very open to any kind of collaboration within our bench. We can provide expertise on especially cryogenic engineering, cryocoolers, ADR system, and also getting a partnership. So feel free to reach out to the website and feel free to reach out to me or our bench at very so. Yeah, that's all about it. Thank you. Any questions? Sorry if I rushed through it. I didn't know like time is like so restricted. Just want to give a lot of information.
We want to have time for one question.
One question, I have a question about the heterostructure. So I believe the heterostructure at the apex and galleries is the physical proximity at the crest. Would be the one that would cause diffusion, the PM, or is there any other mechanism? So with the strain, I believe the interlayer interface would be more physically exposed to each other.
Yeah.
Is that the main cause?
No, that's one of it. That's why we stay at the crest. The interlayer coupling is stronger because the interlayer distance is actually shorter. So it's a Poisson line effect.
Yeah.
So that's one part of it.
This is our speaker.